Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman Ahmad Shukri, alias Kuapitel. My title is Electromagnetic Performance of Cemented Stator Flux Switching Permanent Magnet Motor. My supervisor is Prof. Madya IR Dr. Irwan bin Sulaiman. For the introduction, flux switching permanent machine is a brushless machine of stator type permanent magnet machine. Cemented stator flux switching permanent magnet machine is electrical machine with two or more cemented stator parts separate. That means that there are two and more cemented or two and more partition stator part in that model. Advantage of flux switching permanent magnet is high torque density, good thermal management, low magnetization, and suitable for high-speed application. For example, high-speed application is electrical vehicle. This result will focus the design structure and performance of flux switching permanent magnet, cemented stator, and conventional stator. For the problem statement, conventional flux switching permanent magnet machine has many advantages. It also has certain downsides. That downside are flux linkage, longer flux path, and drop performance at stator part when one of stator core is brought down. Because of this downside, this project purpose to evaluate our cemented stator flux switching permanent, which can increase the flexibility of stator coil and will focusing the issue electromagnetic performance. That means that cemented stator is purpose to reduce the downside of conventional flux switching permanent magnet. The objectives of this project: first, to design cemented stator flux switching permanent magnet. Second, to analyze the electromagnetic performance of cemented stator flux switching permanent magnet on the issue relating to stator cemented technique. The last one is to compare the electromagnetic performance of conventional and cemented stator flux switching permanent magnet. For the operating principle flux switching permanent magnet, there is basic operating principle. The field winding coil is fed with direct current continuously, while the ammeter winding supply DC according to the position of rotor. The flux enter from stator pole to the rotor pole and exit at the aligned stator as shown in figure A. So that means that this is stator and this rotor. The flux will enter from stator to the rotor and exit to stator. So direction is clockwise. As you can see, the ammeter coil and permanent magnet is positive direction, and the flux will be negative direction. So at the same instant, with the permanent magnet having a constant direct current, the polarity of ammeter coil turn to receive the direct current by switching the flux enter from rotor pole to the stator pole and exit aligned rotor as shown in figure B. So we'll be switching the position. As you can see, right now the permanent magnet and armature is negative direction, and the direction of flux is positive, and flux will be enter from rotor to the stator and exit to rotor back. And that's a meaning of flux switching. For the model design, we're choosing the 12 slot 14 pole as our design. So this is conventional flux switching magnet. This is basic model 12 slot 14 pole, and for the cemented, we divide by 2 cemented 12 slot 14 pole, and for the 4 cemented we divide by 4. This means that there are 4 partitions here. For the methodology, in this project we using two software, JMac version 16 software to design and simulate. And the second software is Microsoft Excel for processing data to generate graph and value calculation. So this is flowchart of JMac version 16. JMac version 16 have two parts, Geometry Editor and JMac Designer. Geometry Editor is using to design the model, while the JMac Designer is to simulate the model. For Geometry Editor, first design rotor, after that magnet design, and that stator design, and last one is emitter coil design. And after we finish design the model, we upload save to JMac Designer. At JMac Designer, we set up the material and we set the condition. After that, we set the circuit, single phase or three phase. After that, we set the properties, and after we set the property, we mesh and we can run the analysis simulation. If our simulation can run without error, it will display the result. For the result analysis, we have two analysis, no load analysis and load analysis. For the PSN1, I only doing the no load analysis. For the analysis, this is conventional 12 slot 14 pole. We must run the simulation 12 coil arrangement test. To test our model is correct the parameter and good condition. As you can see, we get this result. After that, we must combine 12 coil to 3 coil to generate this result. And after we get this result, we doing the UVW test. This means that we're using the 3-phase circuit in this result. And after we get this result, we're doing the zero rotor position. From the zero rotor position, we can see the center is 16 degree and the center is 180. The different distance is 120. So that means this is the good result we get here. So after we get this kind of result, we can generate the coking torque. And this is the coking torque. We get 6 speed here. This is 1 cycle and this is good result. For 2 segmented 12 slot 14 pole, we run the simulation 12 core element test and we get this result. Actually, this is not a good result because the pattern is not the same and not symmetry. So we combine 12 coil to 3 coil and we get this result. After we get this result, we using UVW test and using 3-phase circuit to get this result. After that, we must do zero rotor position analysis. The difference between center to center is 120, but in this result, the center to center is not 120. After that, we doing the coking torque to see that our result is okay, is good or not. So for the coking torque, we can see the result is not good. This because 12 slot 14 pole is not suitable for 2 segmented. So there are suggestions for change to segmented 12 slot 14 pole to segmented 12 slot 10 pole to get the best result for the to comparison the conventional flux machine pneumatic motor. So that's all for me. Thank you.